This is a continuation of notes 14.3. We had problem number 5 that we're working on, and let's show you where we got what we have right now. The differential equation y prime was given to us. Y prime is the reciprocal of x squared plus 1. We were given the initial conditions x equals 0, y equals 0. That's shown in our table here. We also found dx by a simple calculation of our initial x value and our ending x value, the value that we're trying to get our estimate on. That gives us the difference between the two x's. x1 minus x2, or a b minus a, the language or the terms we used last year. That being 1, we were taking 5 steps, so 5 is our denominator, so our dx each time is a constant value of 1/5 or 0.2, and that's shown here in our table. To explain where we got the other items in our table, remember y prime comes from the equation here, substituting in each x value, squaring it, add 1 to it, and the reciprocal. Our first y prime value is 1. We use the dx and the y prime value to find dy. dy is a simple calculation of y prime times dx. 1 times 0.2 gave us 0.2. That dy value is added each time to the previous y to get the new y. Our x values, we're just adding dx each time. Each one of these are the exact same amount. The dx value does not change. We added it 1, 2, 3, 4, 5 times. Those are the 5 steps. We have to calculate our dy each time. That's why we're using this table, so we know what to add to the previous y value. When we added the 0.2 to 0, we got 0.2. Then we put this 0.2 into our equation, the x value, squared it, add 1, took the reciprocal, and got 0.9615. Multiplying those two numbers together, we got our new dy value. dy is added to the previous y value. 0.2 plus this 0.1923 gave us the 0.3923. 0.4 in our equation, squared plus 1 reciprocal, gave us our new y prime. Y prime times 0.2 gave us this dy value. Added to the previous y value, we got 0.5647. 0.6 squared plus 1 reciprocal gives us a y prime value of 0.7582. We'll multiply that again by 2. That'll give us our new dy value. Our new dy value will be 0.14705. Add that to our previous y. This will give us 0.7117. 0.8 squared plus 1 reciprocal gives the new y prime value of 0.6097. Multiply that number times 0.2 gives us our new dy. This one happens to be our last one. This will be our last step. We'll add that value to the previous y, and that gives us the estimated value of 0.8337. y1 of sub 1 is going to be approximately 0.8337 using the Euler method. In our notes, it asks us to do that in part A, and then in point B, it said let's find the value of y double prime of x. What will that be? Let's recall how we did a few of our derivatives. We know the first derivative. We want to find the second derivative. So we'll take the derivative of that. And it's probably easier if we consider this as y prime equals the quantity of x squared plus 1 to the negative first power. So we take the derivative of that to find y double prime. This will be x squared plus 1 to the negative second power times the negative 1 times the derivative of the inside, which will be the derivative of x squared is 2x, the derivative of 1 is 0. That could be rewritten to match the answer in the answer document or on a multiple choice test, their answer. Negative 2x in the numerator, and in the denominator we'll have the quantity of x squared plus 1 to the negative second. The next thing it asked is for what are the concavity intervals. What are the concavity intervals? Remember, when we're looking at concavity intervals, we're looking at y double prime. Where does it equal 0? Or where does y double prime not exist? To consider our zeros, we look at the numerator, and in that case, you can quickly see that x equals 0 will give us y double prime equal to 0. And then our does not exist, we look in our denominator, and this has no problems in here. There will be no undefineds in that, so that would be our null set. So our concavity at x equals 0 is going to be 0. Let's take a look at this equation, and when x is negative, our y, or f, I have it here as f, but our y double prime is going to be positive. Our y prime, double prime when x is positive, will be negative. Just checking the values here in this equation, which tells us that we are going to be concave up on the interval from negative infinity to 0, and we will be concave down on the interval from 0 to infinity, both of those being open intervals. Part D in our notes asks us to consider, is our estimate too high or too low? Okay. Think of concavity. We are going to be too high when we are concave down. Our tangent lines will always be above. Remember, Euler's method is using this tangent line, using the slope of the tangent line to advance to the next point, and then changing the slope from that point, and changing the slope on. If we are concave up, then our tangent lines are always going to be below the curve, and we're going to be too low. So if we are concave down, concave up will determine if we are too high or too low. Our estimate was that x equals 1. At x equals 1, we are going to be concave down. Why do we know we're concave down? Because y double prime is less than 0. When y double prime is greater than 0, we're concave up, which can tell us for sure that our estimate is too high, because y is concave down at x equals 1. If you look back on your notes, there's a quick little comment here that be careful about rounding. Now, to help you out with this, on your calculator, use that answer key, second, and using this second option on that key allows us to use that previous value. So you can see I went through this rather quickly, but I could be getting 5, 6, 7 decimals in here, which if I truncate these each time, I'm going to be getting a lot of error in my calculations. So and just reuse this value. Take the previous value times 0.2, keep that in your calculator, add that to this value, and then continue on. Okay? Storing values and saving values and using that answer key is going to save you a lot of trouble and will get you closer to where you need to be. To finish our notes, you'll see what we've done is summarized here in the steps of Euler's method. Use your initial values, find dx. Remember, that was simply that calculation of b minus a divided by the number of steps. Build your table, putting in your initial values. In column 1, in column 2, you're going to have 2 columns in there, which you're going to fill out those values as you go, your x's and y's. Your x's are just adding dx to them each time. Your y's are taking the previous y value and then adding dy. Remember, dy is y prime times dx. That's what we're showing here in the formula. And a final statement, to make Euler's method more accurate, we decrease the size of dx or increase the number of steps.